okay. Well, yeah. Okay, so this is chapter 5 review. And section 5.1 was about finding the area under a curve. Now you guys have notes, and you have example problems. So you can actually go back and do that. And what we did is we put rectangles under the curve to estimate the area. Okay? That's all it is, base times height. Now you have several different kinds of rectangles. There's 3 different kinds you can have. It's not like I've memorized this. And so we will tell you to divide it into 3 rectangles or 4 rectangles. It won't be any worse than that. And we'll say, use the left Riemann sum. Andrew, do you know what that means? Okay, so if you take a curve and you put you're going to try to estimate the area. And here's my curve. And you're going to divide this into rectangles. Let's just divide it into 3. Then I want my rectangle's height to be determined by the left side of my rectangle. So I go up the side with the left and draw my rectangle that way. How do I know if it's an overestimate or an underestimate? I draw the picture. Well, it depends. Yeah, that's what I said. I just look at the picture. I haven't really memorized when that happens. So this is what our book calls LRAM, but it's a left Riemann sum. If I want to right Riemann sum, I'm going to draw my rectangles, and I'm going to take the right side of my rectangle, and that will be the height. So that's going to be an overestimate with this particular function. Pardon? The middle one is the best one, and I think it's probably maybe the one I've seen most common on the exam, or we could do trapezoids. So here you have your rectangles, you have the base there, and then you find the middle of it, and you go up to the curve, and that's the height of your rectangle. So some is usually over, and some is usually under, and so it actually gives you a really good estimate. I'm going to find the middle here, and that's going to be the height of my rectangle. You see, it's sort of halfway between. Some people say, well, isn't it just the average of the left and the right? I don't know. I never thought about it that way. I'd have to prove it to believe it, to tell you the truth. It looks like that might be the case, but I'm not sure. So the red is the right Riemann sum, and the green is the midpoint. No, because if the question says, like if you look at we're not there yet. This is what 5.1 is. If you look at this TAN worksheet or whatever color you want to call it, it says use a midpoint Riemann sum. So that's what you're going to do. You don't have the functions. You can't do an antiderivative. So we could do any of these problems. Well, that's what 5.1 is about. Just estimating using rectangles. Any one of those possibilities, left or right or midpoint. Then in section 2, we define an integral. Again, it's still using rectangles, more or less. And so the Riemann sum call it definite integrals. And my guess is what happens is these guys kept adding up the rectangles, and they said, I don't want to write this out, because what you're really doing, the calculus here, is adding up all the rectangles. Well, that's base times height. So we're going to call it x sub I and delta x. And we're going to add them all up. That's what that sigma does. And we do a lot of that in BC Calc. We do a quarter's worth of material on that, so it's hard. But that's not really where we get stuck on. But we're going to add up the base and heights of all my rectangles. And if we keep all the bases the same, I can put an infinite number of rectangles in there and fill up all that space there. So we'll take the limit as n goes to infinity. We never did that by hand. But we talked about it. Does that make sense? That if I keep putting more and more rectangles, that's the calculus. I'll put an infinite number of rectangles. That's going to all be shaded. Okay? And Riemann Riemann says, I don't want to write that every time. And I don't know if it was Riemann, but probably gets credit for it. He made up a little symbol. All math is made up. Yeah, it's a language. So you just have to learn the language. And he said, let's just call that the integral from a to b of f of x dx. That is a definition. Somebody made up the symbols, and it's called a definite integral. That's why I have that written there, because you have a definite beginning and a definite ending. So I don't want to write all that, but that's what this means. So when you come into the exam on the multiple choice part, and it's going to be a hard question, you may see something that looks like this, and you're going to have to figure out, oh, it's just this function. I'm going to integrate it from a to b, and I'm on my way. You do not want to do these limits. They're not easy to do. And then, after a while, well, let's go ahead and put it in here. They decided, they saw a pattern here. After they did all these rectangles, they realized, and this is a theorem, that all they had to do was find the antiderivative of this and evaluate it at the endpoints and subtract them. And that's the fundamental theorem of calculus. And that was in section, a little bit in 5.3, or most of it in 5.4. Is that okay, Andrew? Okay, so all you're going to do is add up areas of rectangles. So that's not too terribly difficult. And then here we actually go to an antiderivative. But you have to know what the symbols mean. So what does this integral mean? Because I can't emphasize that too much. The integral from a to b of f of x dx. What does it mean? What are we going to find? To find what? I can find it by using the fundamental theorem and finding the antiderivative, provided the antiderivative exists. It might not. Very hard to find antiderivatives. But what does an integral mean? It's the signed area. That's good. Area is good. Signed area under the curve. Signed area that's trapped between the function and the x-axis under the curve from x equals a to x equals b. I could use my magic pen. That's what it means. So when you see the integral, you can either do an antiderivative, if you can do it, or you can just find the area. It's the same. So how did they get the area of a circle? You could do this yourself. It's a very tricky proof. But you know, the area of a circle is what? Pi r squared. You have to know that. You have to know circumference. You know what circumference is? 2 pi r. How did they get that? We can measure and do that. But the area of a circle, you can divide it into all these little pieces of pi. Sorry for the pun. You can catch it. And the more, you have little triangles here, don't you? I think I'd fail miserably. You add up all those areas. What if you make the pieces of pi smaller? And you take the limit, you will get the area of a circle. You'll actually get this formula. Pi is basically, if you define it, circumference divided by the diameter. Well, it's an irrational number, which is very strange that you could pi is equal to the circumference divided by the radius. I don't know. I'd have to do some more studying about pi. There's a lot of interesting things. Diameter. Sorry. Right. C over D. And you're still there. Okay. What you need to know is an integral is a signed area. This is kind of interesting. The proof is tricky. Very tricky because it involves limits. But if you're ever interested, I can show you that because you can understand it. That's what's interesting about it. You're going to have to use trigonometry here. So I know how we love trigonometry, right? Okay. So that's what, oh, and then also in 5.2, we use our graphing calculator. Do you remember how to do that, or do I need to review that? Graphing calculator. To find integral, which is an area. It's FNING, for most of you with an 83. And the book calls it n-int or something like that, I don't know. And then I like to put my function into y1, because then I don't mess up with the parentheses. Comma x, you have to say what the variable is, from a to b. How does that differ from n derived? The derivative. And if it's in the calculator part, you want to use the calculator. Even if you can find the derivative by hand, and you're given a calculator, it's perfectly acceptable. It's y1, comma, x, comma, at the point. And you could, if I, that was a VC test, if you want to actually graph the function in y2, you could put in n derived, let's say my function's in y1, comma, x, and that actually graphs the derivative function. You can do the FNINT, which is accumulating your area. I've never gotten it to work, but you're supposed to be able to do that. So you're going to graph the derivative function. Is that money going to become mine? Okay, that's all there was in 5.2. And if you're given the absolute value or the greatest integer function, you're going to use geometry. And they're probably not going to give you those. They're going to give you circles and triangles. And then in 5.3, these were the properties. I'll just go in order. These were the properties, even though we didn't learn it in order, of integrals. So if I have a constant integral, if I want to integrate k times f of x, do you remember what we can do, Alex? We can pull the what out? K. Just like derivatives. These are the big ones. I'm not going to review all the properties. If you have the sum of two integrals, you can break that, and that's something you need to realize, into two parts. Now, this little s with the dx, that is the symbol for antiderivative. Okay? That's just the symbol. You're always a victim. dx. So some of you go, well, where does, and we will mark it wrong. If you integrate and you leave the dx and the integral symbol in there, you've used it up. Like when you do the square root of 4, that's just 2. You don't say it's the square root of 2. Do you? Yeah, some people do and they get it wrong, unfortunately. This is the operator. This says find the number you multiply by itself to give you 4. Well, it's just 2. Same thing here. If you see this little s with the dx, it means find the antiderivative of whatever the function is. So there's my function. Find the antiderivative of that. It's used up. If you put your money in the pop machine, you get the pop back out. It's used up. Should I put this someplace else? Okay, so this one can be written as the integral of f of x dx plus the integral of g of x dx. So and you can do minuses as well. So add, subtract. We do not have a property for multiplying two functions together. We're going to have to figure out what to do with that. There is no quotient rule or product rule. Is that okay? There is no quotient rule or product rule. Okay. And there were some other things, but there's the big theorem in this one, I believe, and that's the mean value theorem. And actually, they introduced the second part of the fundamental theorem of calculus. I did not do that. Okay, there are 5 theorems to know. The fundamental theorem of calculus says the integral from a to b of little f of x dx is equal to capital F of x, capital F of b minus capital F of a, where f has any antiderivative. Okay, that's the fundamental theorem of calculus. We have the mean value theorem. We have the intermediate value theorem, and I don't believe it's on your test. And everybody knows it's MVD. So when you use that on your free response questions, and I've seen it several times. Okay, guys? And that's what you don't want to listen, but this is a big test coming up on Tuesday. Okay? And if you run into this on the free response, you just do MVT. To use the mean value theorem, you must have, well, that's not true for that's true for the derivatives. We're going to do the integrals. It is the same thing. But in April, I'll come back again to remind you why it is the same thing, because you'll forget. And all that says is if I integrate from a to b, f of x dx, that's equal to some y value times b minus a. We don't use the mean value theorem in that form very often. We use it in the other form. Solve for f of c. And what do you get, Eva? You get the integral. I want to solve for this guy. F of, you take the integral, f of x dx, and then how do you get f of c alone? Divide by what? b minus a. Also written, it's the same thing, also written like this. Some of you think it's different, but it isn't different. That's exactly the same thing. It's just written a little neater, that's all. Another name for this is the average value of the function. You will see that word, and you will see average rate of change. And let's go ahead and contrast those. They are the same thing, but one's in a derivative form and one's in an integral form. This averages the values of the function. What's an average rate of change? And so you have to really focus on this word. If it says average value, it's an integral. If it says average rate of change, Andrew, what is that? What's a rate of change? You can help them. It's a slope. Average, though. It's the average. So it's the change in y over the change in x for the interval, which is f of b minus f of a all over b minus a. And if you think about it, it kind of looks like the average value. That's an integral. This is not. This is just taking the slope of the secant line. Instantaneous rate of change is what? Yeah, that's the tangent. Here's the key word. It's rate. The minute you see rate, you're going to be doing slopes. Can I get some money? Okay, that's the derivative with respect to x, f of x. Or with respect to whatever you want to find it. It could be t. And the mean value theorem for derivatives says that this derivative equals that average rate of change. And I'm not going to connect them right now unless you want me to, but they are connected. It took me a while to connect them. And especially on the exam, because they're going to ask you for average value of a function. Well, it depends on what you're given as to if you're going to integrate or actually find the slope. Because if I want the average velocity, there's two ways to do this. The average velocity, I could add up all the velocities from t1 to t2 over t2 minus t1. I just said I wasn't going to do it, and I'm doing it. If I want the average velocity, and I'm not given the velocities, but I'm given the position, it's also equal to the change in the position divided by the change in time, which is s of t2 minus s of t1 over t2 minus t1. What's the antiderivative of the velocity? The derivative of what gives you a velocity? Position. So they're the same, but it depends on what you're given. If you want the average velocity and you're given velocities, you integrate. If you want your average velocity and you're given position, you find the slope. So you may have to look at this again. Okay, that's the mean value theorem. Now there's bells. And then we go to 5.4, which is probably the most important one, and that's the fundamental theorem of calculus. And I've already talked about that. Then there's another fundamental theorem of calculus. We call it the second fundamental theorem. Different books label them in different ways, so don't worry about it. They're both the fundamental theorem of calculus. And that's what that worksheet is. What is the derivative with respect to x of the integral from some constant to x of f of t dt? We could put in x's here, but it gets confusing with the x. That's the reason why they're t's. What happens if you take the derivative of an antiderivative? They cancel out. They're inverse operations. So you just get f of, but if we were to integrate it, you would have put in that upper limit. So it's not f of t anymore, it's f of what? F of x. Well, that's how you do the back, well, that's how you do this whole worksheet for the most part. Which one? E? Oh, okay. Actually, it works out nice, but I'll do it the proper way. Right. Times the derivative of x with respect to x, which is what? 1. So I don't have to write it, but I like to have it there because what if you take the derivative, we're going to do e in it 1 second here, from a to g of x of f of t dt, what are you going to do? This is not going to be f of x anymore. It's f of what? No, you have to take this, whatever's there, and put it in there for t. So it's f of g of x times g prime of x. If you go back and look at the video, I actually proved why it is what it is. So the question comes up, and I've never seen these on the exam, but on this worksheet I just gave you, it's d dx of this. You could integrate it, but why do that much work? That's too much work. So this has to be a constant. So what we can do is we can break this into 5x to some constant. Should we call it little c? I don't know where it is, but there's a number in between those two things of cosine of t. It's kind of weird, but okay. Plus, and then, and part of your test is AP, part of it's not AP, part of it's just standard problems. And then we'll go from the constant to x to the 4th. Because remember, when we find the area, and I didn't do this property, but if I find the area from A to B plus B to C, I get the area from A to C. And this is cosine of t dt. Now, I've got a little problem here with the first one. What's wrong with that? My theorem starts with the constant. My theorem does not start with that variable. So if I switch that and put the c and the 5x here, what happens to my integral? It becomes negative. And that's cosine of t dt. And I do believe you are going to find some problems on your test like this, if I'm remembering the test correctly. Plus. And then we're going to do this one. Let's just do it all in one line. And once we get to this stage, I really just have two problems on the fundamental theorem. So what's this going to give us? The derivative of this is going to give me the negative, and what are you going to put in for t? 5x. Is that okay, Andrew? So I expect a perfect score on this part from you. Times what? Got to do the derivative of this 5. I don't care. We're not going to simplify it. Because the theorem goes from the constant to the function, not a function to a constant. And we originally had a function to a function, and I don't have a theorem for that. So how are you going to handle it? That was the question. That's the reason why I'm doing it. Not unless you write a theorem. You could. I'll leave it up to you to do that. And what's this one going to be then? We put x to the 4th in for t. Sorry. Yes, cosine of x to the 4th times the derivative of x to the 4th, which is what? No, 4x cubed. Not if you practice. Like, do homework. Do that worksheet. Why? Remember, this is your job. You want to do this, get your credit, and be done. For some of you, if you're pre-med, you have to get two full years of calculus. So if you do AB and BC, you're done with 1 year. You have to go back and do some more. It depends on what you want. Okay, so that's what we do with those. That's it. It's easy. If you think about it, it makes sense. If you want me to prove it again, I will. And there's one last topic, which is section 5.5, and that was the trapezoidal rule. And you have to know that formula. What is the area of a trapezoid? Now, our trapezoids are not going to sit on their bases. That's height, that's base 1, base 2. Andrew, do you know the formula? You have to know this.
1/2
B1 plus B2.
See, I told you.
And you just fit trapezoids underneath there. That's all.